Our next unit is going to be all about functions and what we call mappings and transformations, and we're going to be going over what those different things are, and eventually in this unit we'll be getting into the types of transformations that we'll be seeing a lot of in geometry, which include things like reflection, rotation, translation. You'll hear me say those words a lot as we get going in this unit, and you'll be able to perform those types of transformations by the time that we get a little bit farther in here. To get started with today, though, we're going to focus mainly on what a function is. So before we get too far into this, let's just remember what a function is. Now, you would have seen functions last year when you were in algebra. Functions are a way of talking about an equation, and that could be an equation of a line, it could be an equation of a quadratic, like a parabola, anything like that. Specifically, what we're going to be looking at in geometry is how two sets, so they'll maybe call set A and set B, or they might use other words like input, output, and we're talking about how they relate to each other. So you see here where it says it's a correspondence between two sets A and B, and what makes it a function. So it is a function if and only if, so notice how this is like bold, capitalized and underlined here. If and only if means that this has to happen or else it cannot be considered a function. So there is no excuses here. You have to have these things be satisfied in order for you to be able to say, yes, it's a function. So a correspondence between two sets, A and B, is a function if and only if every member of A, so every member of set A, corresponds to one and only one member of set B. So what that means is when we look at our sets, and they're going to be, like you can see down here, in this case they've got letters, but they could be using numbers when we're looking at maybe a specific graph of a line or something like that. What they're going to look for is if you have like X values and they're going to Y values. So let's say set A represents your X values and set B represents your Y values. You want to make sure that all of those X values only go to one and only one value in the second set. So in that case, the Y's. So you want all of your X's to only go to one spot on the Y. In this case, down here you see everything from set A, only one of those can go to one item on set B. I want you to think about it like this with me for a second here. When you come to school and you start going to your classes, you have to choose what class you're going to go to based on what your schedule says, right? So you can't be in math with me and be in English with your English teacher at the exact same time. It just doesn't work that way. Your period 2, for example, is dedicated to a specific subject. You don't get to just choose that you get to go to 2 classes in one period and then get to have a free period later. So that's kind of what we're talking about here with these functions, is that you can only go or be in one place at one time. When we look at our first set, those values can only go to one place in the second set. So imagine that you are a person in set A and set B is a location that you're going to. You can't split yourself and go to 2 different places at one time. It's just not possible for us to do that. And that's kind of an easy way for us to maybe think about how we can relate ourselves to what a function means when we're talking about mathematical terms here, okay? So the first thing that we're going to do on these examples down here is we're going to see if they're functions or not. Some other words, some other vocab words that you maybe need to be familiar with are these 2 words here where it says domain and it says range. Domain would be your X values. So again, going back to our algebra thinking when we talk about graphing a line or graphing any type of function, you had X values. You know, you have equations that say 2x plus 5, or maybe it's x squared minus 3 or something like that. X is going to be your domain, because that's going to be what you put in to the equation. So you can put in a 0, a 1, a 2, a 3, a -1, a -2, a -3. The Y, which would be your range, that's going to be what comes out. So when you evaluate the equation at a specific x value, what do you get for an answer? That's going to be your y. So when we look at these, sometimes they'll have it written as like set A and set B, but even down here on your notes, you can maybe see these words domain and range showing up. And so that's just another way that they're going to differentiate those parts of the functions that we're looking at, so that you know this is the x values and this is the y values, or this is where we started and this is where we ended. Okay? All right, so when we look at these and we're trying to decide if they're a function or not, we need to look and see, does everything from the first set go to only one location on the second set? So you're going to see like there's arrows being drawn from set A to set B on these first 4 examples. What you basically need to make sure is that everything from set A only has one arrow coming off of it. If anything from set A has more than one arrow coming off of it, then it's not going to be considered a function. Okay? Because you're trying to split yourself and go into 2 places at one time, and you just can't do that. So if we look at number 1, I have A going straight to D, that's got 1 arrow. B is going straight to E, again 1 arrow. And C is going straight to F. Okay? That's also got 1 arrow. This one would be a function, so we should be able to circle yes. Okay? And why? Well, each element, so I'm just going to write this out, each element in set A goes to 1 in set B. Now, eventually, we're going to start talking about what type of function maybe something is, and we're going to use some more language to describe that, to kind of give you a little preview of what I mean. This specific function would actually be considered a 1-to-1 function, because that means that everything from the first set goes to its own unique location in the second set. So A goes to D. Nothing else is going to D. A is the only thing going to that. So think of it like this. When you come to school with maybe 2 of your friends, maybe you go to Spanish first period, your first friend goes to history first period, and your second friend goes to math first period. Okay, you each have your own location that you have to go to. No one's going to the same class at the same time. So that's what we mean when we say a 1-to-1 function, and we'll talk more about that in detail a little bit later. What I want you to do right now is I'm going to give you a little bit of time here. And just a reminder, if you need to pause the video here to give yourself some extra thinking time, that is fine. I want you to do 2, 3, and 4 by yourself. I want you to decide if you think it's a function based on the things that we've talked about so far. And if you're saying yes or you're saying no, I want you to give me a reason why. Why do you say yes? Why do you say no? So go ahead and take about a minute here or so to do that. All right, as I said earlier, if you're not quite ready, go ahead and pause the video here. I'm going to start getting into the explanations. Otherwise, this video will be a half hour long by the time I get done if I pause for everything. Okay, so number 2, hopefully you noticed that A is going to D and it's trying to go to G. So we've got 2 arrows coming off of A, which we said is not allowed. So we need to say no, it is not a function. And that could be your reason. A goes to D and G. And so that would not be considered a function just based on that happening there. Okay, number 3. A goes to D, B and C are both going to F. Now, be careful with this one because I could see some of you circling one of those 2 answers because maybe you're misunderstanding what it means to be a function. Remember, what we said is that everything from set A needs to go to one location, one point on set B. Okay? So some of you might have thought no, because you see that B and C are both going to F. Okay? But think about what we said when it needs to be a function. Do any of those letters, A, B, or C, have more than one arrow coming off of them? Hopefully you're thinking, no, they all have one arrow coming off of them, okay? So this would be another example with you and your friends, okay? You come to school, you're A, and you have to go to Spanish, and you have two friends, and they both get to go to history, okay? It's okay if you have points, multiple points going to the same location, because there's a whole bunch of us right now in this classroom, and we're all here together doing math at the exact same time, and that's okay because we're not trying to split ourselves to going to two different locations. So this one is actually a yes. Okay, so if you said no, that's okay. That's a common thing that we see kids get a little bit confused on. But this one has, again, kind of each element from A is going to one element in B. So this same reasoning up here, so these words up here, you could have written down here as well. And just to save some time, I'm going to just circle and draw an arrow, okay? Number 4. Hopefully you circled yes on this one. Okay, this is very similar to that last one there. A and C are going to G, but again, A and C only have one arrow coming off of them, so that's okay. So once again, I'm just going to kind of shortcut my way here. We can use the same reasoning for this one. Each element in set A goes to one in set B. Oh, maybe as you guys were looking at those, you maybe saw an easy way to determine if something was a function or not. You maybe start to notice a pattern or something that they always seem to do when we had to say yes, or always seem to do when we had to say no. Okay, so if you can think of something like what's an easy way to determine if something is a function or not, just by looking at the picture, I want you to take a second, just write down what you think maybe you're noticing, if anything. So something that I noticed, and I kind of was saying this a lot, was those arrows that I was talking about. If a point or a letter or something like that in the domain, so in the first set, has more than one arrow coming off of it, it's going to automatically be a no. So we're going to say if a point in the domain has more than one arrow, I'm running out of room here, then it is not a function. So if a single point from the first set has more than one arrow coming off, it could have 2, 3, 4, 5, it could have 100 arrows coming off of it. If you see that, it's got to be a no, because you're trying to take that point and split it amongst multiple places. And again, if we think about ourselves in this situation, I can't be here in this room and be in another room in the school. I just can't do that at the same time. Another way to think about it is you can't be at school and be at Walmart or be at the grocery store or the doctor's office at the same time. You have to choose a location to be at. So you can't have more than one arrow coming off of those things. So maybe if you start to look for that, it'll make some of these problems go a little bit quicker now, because you'll maybe start to just be able to look at the arrows. You won't have to think so much about the letters or the numbers that they're giving you. Just look at those arrows and use them to kind of help you make a decision about whether you think it's a function or not, okay? So, using that now, kind of that thinking, they've got a couple more here, 5, 6, and 7. Now again, these are written a little bit differently. Instead of saying set A and set B, they say domain and range. And they've got numbers instead of letters. It doesn't make a difference though. We're not worrying so much right now about what the functions are maybe looking like on the graph. We're just trying to decide if they are a function. So, using what we just talked about, if a point has more than one arrow coming off of it, then it's a no. Okay? And if every point in the first set has one arrow, then it's a yes. I want you to quickly answer 5, 6, 7. It should take you no more than 30 seconds here. Okay, for number 5, hopefully you said yes, because they all have one arrow coming off of them. Number 6, you should have said no. The reason why is because 2 is trying to go to 7 and 3. We can't have that happening. And number 7 should have been another yes, because they all have one arrow going to that location. Okay, now what we're going to get into is some more of the technical vocabulary that we're going to be using when we talk about these functions, specifically what are some of the things that they should be doing, or some of the language that we can talk about in describing what's happening within our function here. Okay, so the first thing we're going to talk about is something called a mapping. So what is a mapping? That's a new word for us. A mapping is a correspondence between the pre-image and the image. Okay, and it's a mapping if and only if. So again, we're seeing that word where this has to happen. Okay, if and only if each member of the pre-image corresponds to one and only one member of the image. Okay, so here's what that means. The pre-image is going to be where you began. So what you started with, and the image is going to be where you ended. So the pre-image would be your domain, and the image would be your range. So where did you start? Where did you end? Now, if you can take, like the shapes that we're going to see here, they're going to have corners or points in that they use to kind of label the vertices. If you can take a single point from the first shape and match it up with a single point on the second shape and everything gets a pair, then you should be able to say that it's going to be a mapping. Okay? If we can't do that, then we have to say that it can't be. Okay? So let me explain or kind of show you an example of here of what I mean. So if you look at number 8 with me, I see 2 triangles. Now all of these are a little bit color coded for us. So like 8, we've got like a blue triangle, and then we've got this purple triangle. Okay? They're telling us that the pre-image down here, pre-image is triangle KLM. So they're talking about the small triangle here. Okay? What I like to do to try to think through maybe what's happening, like to decide if this is going to be a mapping or not, I like to list out all the points that come from the first shape, and then I like to list out the points that come from the second shape and see if there's a way that I can connect them and make it a function. Okay? So for example, on this small triangle here, I've got 3 letters, L, M, and K, or KLM. However order you want to put it in, it doesn't really matter. So I'm going to write L, K, M. Okay? That's from the first shape. Now the second shape, the purple one, has 3 new letters, N, O, and P. Okay? I could, in theory, say that L went to N, K went to O, and M went to P. Okay? They maybe made the triangle a little bit bigger. They maybe turned the triangle around. Those are kind of those transformations that I was talking about at the very beginning of this that we haven't gotten too far into yet. But all of 3 of those letters, L, K, and M, were able to correspond to 3 other letters in the other triangle, N, O, and P. Therefore, we should be able to say that it is a mapping, so we should be able to say yes here for this one. Okay? Because each point on the pre-image goes to one on the image. Okay? Now, I'm going to look at another one here with you guys. I'm going to look at number 9 with you. So number 9, we've got 3 letters. We've got K, L, and M. Okay, so pretty similar to that first triangle. Now, the second shape has 4 points. It has S, T, U, V. Okay? If I start to draw my arrows, K could go to S, L could go to T, M could go to U, but I still have this last point here that's missing something. It doesn't have anything to go to it. I can't take something that has 3 points and create a new shape that has 4 points and have that work as a function, because what this would mean then is that one of these 3, K, L, and M, in order to give V a pairing, one of these has to have another arrow coming off of it. So even if I said, okay, let's give M another arrow, Well, now M has 2 arrows. It's trying to go to 2 places. It's trying to go to Spanish class and history class at the same time. And we know that it can't do that. So this one has to be a no. This is not going to be a mapping. Okay? And the reason why is we're trying to go 4 points from 3 points. Anytime you look at these problems, if the original shape has fewer points than the new shape, it's going to be a no, because you're going to have one of those split and have double arrows or more than one arrow maybe coming off it. And we just talk about that. That doesn't work. It doesn't happen that way. Okay? So I want you to look at 10 and 11, and I want you to kind of think about what we just talked about with number 9. You know, we said you can't go from fewer points to more points. These ones are a little bit different because you're going from 3 points down to 2 or 3 points down to 1. I want you to maybe think about this, or if you need to, maybe ask your neighbor if you're a little stuck. Do you think that these two work? Okay, because they're similar. So I want to give you guys about 30 seconds here to talk about this, or kind of open it up here and see if anyone notices anything. All right, so like I said, these ones are a little different because you're going from 3 points down to a smaller number of points. So, for example, if we look at K, L, and M, and we're going to Q and R, well, K could go to Q and L could go to R. Well, M can go to one of those two, and it doesn't really matter which one. So you can pick whether you want it to go to Q or you want it to go to R. Let's just say we want M to go to R. Well, if I look there, do all of those 3 letters, K, L, M, only have 1 arrow coming off of them? Yes. Okay. So I think that makes it a function because it doesn't seem that it's breaking that rule where those letters have more than 1 arrow coming off it. So we should be able to say that, yes, this is a mapping. Okay. Because each point, so using this reasoning again up here, each point on the preimage goes to 1 on the image. Again, it's okay if you and a friend both come to math class at the same time. Maybe you have a friend in this classroom right now with you that you guys come to math every day together. That's okay because you're not trying to split yourself to go to multiple places at one time. The same thing's going to happen here with 11. Okay, so if you maybe didn't get number 10 right, number 11 is the exact same thing. It's just instead of going to 2 points, we go to 3. We have K, L, and M, and we're going to T here. This one means that they're all going to T. So everyone's going to the same place. And once again, we can use this reasoning to help us out with that. So I'm going to save a little bit of writing there. But those all work. All right, so if you turn your page over here in your notes, it says at the very top, what's an easy way for us to determine if something is a mapping or not? So this is kind of like, what was an easy way for us to determine if something was a function? And that's when we said, oh, if it has more than 1 arrow coming off of it, then it's not a function. Okay, in all of those that we just looked at with the mapping, if you have the same amount of points, or if you have more points when you begin to than where you start end, then you should be able to say that it's a mapping. Okay, so I'm going to say it's a mapping. So it is a mapping if you start with the same amount of points. So I'll say the same or more points than when you end. Okay, so like on the first one, so that number 8 and 10 and 11, they all satisfy this rule. 8, the starting image and the ending image had the same number of points. They each had 3. For 10 and 11, the starting image had more than the ending image did. That did not happen on 9. Number 9, the starting image had 3 points and the last image had 4. So that went against this rule here. Okay? So just like before, now that we know kind of this shortcut, we kind of recognize that. I want you to look at 12, 13, and 14 here by yourself. And again, this should not take you more than 30 seconds to circle yes or no using what we just talked about there. All right, number 12 should have been a yes. 13 should have been a no. Okay, again, if you count, you have 1, 2, 3, 4, 5, 6 on this one. You have 1, 2, 3, 4, 5, 6, 7 on this one. So you're going from fewer points to more points. It doesn't work that way. Number 14 should have been a yes. So hopefully you're able to get all of those correct. And if not, make sure that you change it in your notes. You don't want to have the wrong answers written down in your notes. Okay? All right, the last thing we need to talk about here today, and I alluded to this earlier, is something called a one-to-one function. Okay? When we were talking back in algebra about functions for the first time and kind of getting into this whole idea of function notation, a function, is when it's called one-to-one, means that everything in the domain has something to go to in the range. Okay? So again, that would be that we all have our own homes to go home to. Okay? When we leave school, we have our own location that we're going to end our day at some point. Okay? And that's going to be different for everybody. Granted that none of you in here are related and are living in the same house. I'm kind of just assuming that everyone's going to go home to different locations. So that's kind of the idea of the one-to-one function, is that everything from the first set of data has something to go to in the second set. And nothing gets shared, nothing gets repeated, or has arrows going to the same location. Okay? So, like you can see on this first one, set A has A, B, and C, and set B has D, E, and F. They all have one arrow coming off of them, so that makes it a function, and they're all going to their own location. A is going to D, B is going to E, C is going to F. Okay? A not one-to-one function. This is still a function, though. Okay, the second one here, because A, B, and C, they all have one arrow coming off of them. But it's not one-to-one because B and C are going to the same location. So imagine this is a brother and a sister, let's just say. They're going to the same home, probably at the end of the night. So that's why this one's not considered one-to-one. It's still a function because it still satisfies the rule of everything has one arrow. But in this case, it's not one-to-one because we've got a couple points that are sharing their final location there. Okay? When we are talking about this in geometry, if you have the same number of points in the pre-image as you do in the image, then that's called a transformation. So like back on the previous page that we were on, at the very bottom there, that one that was 2 triangles, you had 3 points and 3 points. That's one-to-one because each letter could go to another letter on the second triangle, okay? But when we're thinking about it in geometry, we actually call that a transformation, because what that means is I took the original triangle and maybe I just moved it around a little bit. I maybe made it a little bit bigger or a little bit smaller. But when it matches up with the second triangle, everything has a place to go to and it all has a point to share with. Okay, so for example, in this pictures here, a transformation, we've got L, M, N, K, and then they've got these new letters, and notice they've got like these little marks next to them. They have like this L with like this little dash, and M with this little dash. What those dashes mean is that that's the new shape. So that's after we did some stuff to the first one. We changed maybe its size or we changed its position on the graph. And when we talk about that, we don't say, L with like a little dash or M with a little dash. We call that dash prime. So you're going to hear me say L prime or M prime, N prime. I'm going to use that word prime to be talking about the new shape. Okay, so you're going to see that a lot, and it's really important that you recognize this notation because we're going to expect to see you guys use that notation in the future when you start doing your own transformations. So coming forward in this unit, you're going to be doing reflections and rotations and that, and we're going to want to see you put the original down on the graph and put your new one on the graph, but we need to be able to distinguish those. We don't want to just put ABC, ABC, because then we don't really have an idea of, well, which one did you start with and which one did you end with. So that's why we have to use these prime markings. Okay? So you can see how that first one, we have 4 points to 4 points. This next one, we have 4 points to 3. Now, that's still a function. It's just not going to be a transformation anymore because we're changing the overall shape that we ended at. Okay? So a transformation must have a pre-image and an image with the exact same number of points. So take 30 seconds here, and I want you to do 15, 16, 17. Decide if those are transformations or not. Okay, number 15, you should have said no. 16, you should have said no. And 17, you should have said